Welcome to The Explainer. So, today we're going on a seriously mind bending journey. We're going to bridge the deeply familiar with, well, the absolute cutting edge of science. We'll literally start right where you probably left off in high school chemistry, staring at the classic periodic table, and we're going to end up at the extreme edges of modern astrophysics, hunting for dark matter. And the thread connecting all of it? A hidden mathematical code. Now, you might be wondering, what if the periodic table has a hidden statistical code? Think about Mendeleev's famous arrangement for a second. It is a total triumph of chemistry, right? We're all taught that it's neatly organized by atomic number, the number of protons, and that it groups elements by their chemical properties. But what if there's a deeper, mathematical secret running the show here? What if beneath all the complex quantum rules, there's just a pure, predictable statistical regularity governing the literal building blocks of our universe? To really grasp why this matters, we actually need to look at the age-old problem of induction. Basically, how do we predict what we've literally never seen? In a fascinating 2020 paper, researchers actually framed this problem using that famous Donald Rumsfeld quote. You know the one? There are known knowns, there are known unknowns, but there are also unknown unknowns. Well, when scientists are out there hunting for brand new elements to slap onto the periodic table, they are facing those unknown unknowns. Mendeleev's periodic law succeeded because it created kind of like a mathematical tunnel. It converted those unknown unknowns into known unknowns. And as we'll see, modern math makes that tunnel unbelievably precise. Section 1. The table's hidden math. Let's uncover the pattern beneath Mendeleev's creation. So in a massive 2020 breakthrough, researchers Da Silva, Matsushita, and Silva decided to look at the periodic table not just as chemists, but as statisticians. And they discovered something wild. The elements actually follow a power law. If you need a quick refresher, a power law is basically a statistical relationship where one quantity changes as a specific power of another. You find them absolutely everywhere in nature, from the sizes of moon craters to the frequency of words we use in everyday language. In this case, it acts as that mathematical tunnel we just talked about, revealing a perfectly predictable order hidden inside the seemingly complex data of atomic weights. Okay, let's dive into this, because this specific number right here is the whole key. The researchers calculated the Pareto exponent for neutral atoms, and it comes out to exactly 1.0909. Basically, what this means is that as you move up the periodic table, the atomic weight increases as a power of the atomic number raised to 1.0909. It is a stunningly consistent statistical regularity. It fundamentally mathematically justifies why Mendeleev's periodic law works so beautifully in the very first place. And this brilliantly illustrates exactly what we're talking about. Look at this. When you plot atomic number against atomic weight logarithmically, you don't just get some scattered random mess of dots. You get this absolutely beautiful straight line starting right around element 6. This visual proves that the statistical regularity governing the elements isn't just theoretical. It's right there, hiding in plain sight. The math is honestly undeniable. Moving on to section 2, predicting the unknown, let's see how we use this code to find the next element. Now, this math isn't just some abstract concept for us to admire on a chalkboard. It is a highly practical flashlight in the dark for scientists actively hunting down undiscovered superheavy elements. Right now, our current periodic table stops at element 118, oganesson. But by simply using the power law equation derived from that 2020 paper, we can effortlessly predict that the currently undiscovered element 119 will have an atomic weight of roughly 306.54. Think about that. It literally shrinks the massive unknown into a super precise target for experimental physicists. Section 3, pushing to the extreme, taking this from neutral atoms to highly charged ions. We've seen how well this works for standard atoms, but here's where it gets crazy. A follow-up 2026 paper by the same core researchers pushed this tool straight into the extreme edges of physics. So on the left, you've got your standard, relatively calm, neutral atoms that govern all our typical everyday chemical behavior. But on the right, highly charged ions, or HCIs. Imagine an atom that has been aggressively stripped of almost all its electrons. The few electrons left behind are subjected to this massive, completely unshielded pull from the nucleus. They're moving at speeds where relativistic effects completely take over. And standard quantum rules? Yeah, they essentially fly right out the window. It is a totally interaction-dominated, utterly chaotic reality. Section 4. A universal power law. finding order in the sheer chaos of HCIs. Honestly, you would probably assume that in an environment this chaotic, any neat statistical order would just completely break down, right? But the truly incredible finding from the 2026 paper is that even here, the hidden code remarkably persists. While testing a proposed new periodic table designed specifically for highly charged ions, the researchers discovered a brand new scaling exponent, 1.78. So even when atomic mass totally loses its traditional meaning, and these incredibly complex electron correlation effects absolutely dominate everything, the fine structure energy splittings of the atom still bow down to a strict mathematical power law. It's wild. Now, what's really interesting about this slide is how perfectly the data aligns. This maps the energy splittings for transitions between different angular momentum states, specifically from J equals 0 to 4 and J equals 2 to 4. Notice those dashed lines cutting right through the shaded confidence bands? Both of those transitions follow the exact same 1.78 power law regime. Actually, scratch that. It's more than just following a regime. It proves a universal behavior holding firm across an entire sequence of extreme relativistic ions. They only differ in amplitude, not in their fundamental scaling. Which brings us to Section 5, why this matters. We are taking the math to the cosmos. So the crucial point is, why does this heavy statistical physics actually matter outside of a textbook? Because predicting energy transitions in highly charged ions literally helps us unlock the cosmos. Thanks to their super narrow line widths and intense relativistic sensitivities, these ions are absolutely perfect for building ultra-precise optical atomic clocks. Plus, they exist out there in cosmic plasmas, which helps high-resolution X-ray missions, like the XR-SOM space mission, accurately model the universe. And amazingly, networks of these extreme atomic clocks are theorized to be able to detect transient variations caused by topological dark matter. This power law acts as our map, telling us exactly which ions to use when hunting for physics beyond the standard model. If statistical power laws govern both our basic, everyday elements and the extreme ions we use to hunt for dark matter, what other universal secrets are hiding in plain sight? From figuring out the atomic weight of a standard chemical element to selecting the precise relativistic ion needed to trap dark matter, math gives us the flashlight. It leaves us staring into the cosmos with one massive, lingering thought. What else is just waiting for us to find the right mathematical lens? Thanks for joining me for this explainer. Keep asking questions and keep looking for the patterns.